Hello, everybody. Welcome back to Organic Chemistry 1, second Zoom lecture. Once again, we'll be putting it in segments and posting it online. You can find out where these videos are in section 28 of Moodle. At the bottom, there is a document where all of our videos are linked. So please feel free to go there and look at all the videos. And we'll start by sharing our screen here. And let me stop that. I want to make sure the audio is working and my microphone says it is. Try that again. Here we are. I stole some stuff from the textbook. I'm allowed to do this and nobody else is. And here we are. We're looking at chapter 1, Understanding Organic Chemistry 1. You learned about electronegativity back in organic chemistry, chem141, and you learned it was the ability of an atom to draw electrons close to itself in a chemical bond. So species that don't bond, like neon, don't have electronegativities. Other atoms do. The highest electronegativity is fluorine. You have to know these electronegativities. This table is here in the book right in this section, and it appears again later. Just to reinforce, you better learn these. This is like the fundamentals of chemistry, and we need to know especially these elements here because they are the players in the game called organic chemistry. Let me try to make your life a little easier memorizing these. There are some things that have the same number, and let's see what we got here. I used to have highlighters handy over there, and I don't now. That's a highlighter. I think so. Yeah. Okay. Carbon, 2.5. Sulfur, 2.5. Iodine, 2.5. Now, I don't know about your generation, but maybe 10 years ago, there was no less than 3 shows on television called CSI, Crime Scene Investigation. And that is a little memory trick that should help you remember those 3. CSI. The whole second row follows a pattern. You count from 1 to 4 in increments of 0.5. So that's the whole second row. But please keep in mind, this is organic chemistry. Our central atom is carbon. So if you're using this guide of counting from 1 to 4 every time you want to know carbon's electronegativity, that's a little like looking up the word "and" every time you read it in a book. Let's not do that. Let's have carbon 2.5 burned into our brain because that's the one we're always starting with. Okay. That also makes it easier for nitrogen. If you've got carbon in your head, nitrogen right beside it, 3.0. All right, there's some other ones that follow patterns. P and H, and we better learn H. It's the second most important element in organic chemistry. It doesn't follow a pattern with its number, but it's 2.1, and we have to know that. Why is it a higher number? I thought there were trends on the periodic table that said they're supposed to follow an order here, and this doesn't follow the order. Well, hydrogen really behaves not very much like a metal. First column is the alkali metals, and it doesn't behave like an alkali metal in this regard. It does in other regards, like forming ions. That's why it's there. How do we remember P and H are the same? Well, we measure acidity with pH meters. That's got P and H in it. Or if you used to buy calculators from Hewlett-Packard, then you remember HP. Not many people do. Whatever works for you. You've got to learn these numbers some way, somehow. Nitrogen and chlorine have the same number. Nitrogen and chlorine. So think about your finger. You've got a knuckle there, and knuckle sounds like it has NCl, knuckle. And they go together. Just trying to help here. Everybody's memory tricks are different, and something I give you might be useless for you. And what else do we have to do? Any others that are the same? No, that about covers it. So how are we going to do the ones that don't have any tricks? There's only 2 left, it looks like. Selenium and bromine. Well, here your periodic trend is good. Going from row 3 to row 4, the changes are always small. Other changes like size are also small. Whereas going from row 2 to 3, the jumps are pretty big because once you get into the 3rd row, you get new types of orbitals, and that changes sizes, and thus it changes electronegativity. So remember, sulfur and selenium real close, but selenium's a little lower. Chlorine and bromine real close, but bromine has to be a little lower. And if you made the mistake of calling bromine 2.7, I don't think you're going to lose points on my tests because it's having them close that's important. But the 4 that we really care about here are hydrogen, carbon, nitrogen, and oxygen. Sulfur is pretty important. Phosphorus is pretty important. We learned about those in our first lecture. Those are big deals in organic chemistry. Why do we have to learn such things as electronegativity? Well, it tells us if bonds are polar or nonpolar. It's one of the factors that tells us if bonds are polar or nonpolar. If you have a difference in electronegativity, that's what delta En stands for, of less than 0.5, then the electrons are almost equally shared by the atoms, and that's a nonpolar bond. And they're shared, so it's called covalent, which breaks down to sharing of valence. Polar covalent bonds, we have an example of a nonpolar covalent bond here. Polar covalent bond be something like O bonded to H. That's category 2. This was category 1 here. We have a 3.5 for oxygen and a 2.1. Difference is 1.4. And that definitely is in the range of between 0.5 and 1.9. So yes, OH, as suspected, is a polar covalent bond. And it's a very common bond in organic chemistry. Ionic bond. Good example using the numbers we have here. We could have lithium chloride. You could draw it like this, but after you make your calculation, you got 3.0. I always take the bigger minus the smaller, so I don't have negative numbers. Minus 1.0, 2.0. That's definitely category 3, ionic. As soon as you make that conclusion, probably best to erase that and replace it with what it really is. Oh, somebody's talking to me. No, temporary. Hope everybody's okay over there. All right, lithium chloride is not really a sharing of bonds. It's an attraction between a cation and an anion. It's called an electrostatic attraction known as an ionic bond. Textbook has a good example that makes you practice in a big molecule. Just one thing about the example in the textbook, one of the bonds is O bonded to K. Some people start freaking out. Say, wait, I didn't learn potassium, I'm in trouble. Well, potassium's in the first column. It goes hydrogen, lithium, sodium, potassium. So it's 2 rows below lithium. The only thing you need to know is that potassium has to be less than 1. It's following the trend on the periodic table. And oxygen is 3.5. So the minimum difference is 3.5 minus 1, which is definitely 2.5. So it is ionic. So if we have an element not on the list here, then we just use the one in the same column. And remember, that's going to be a bigger number than the one below it. So you're getting a minimum and your actual difference will be larger. So we've got that. I'm going to pause here for a second and get another section from the book. Wish me luck. I don't want to mess up here. Stop share and stop video. I have to remember to start the video. Somebody can unmute themselves and chime in if I screw up and you're just looking at my face. My face not worth much in this course. Looking at what I'm doing is better. Okay, we're going to talk about Lewis structures next. I'm going to steal a bit from the book. We got Lewis structures. And I'm going to bring it over here. I know you don't see anything yet. And now I'll start sharing again. Yeah, there we are. We're there, and I got to share the screen. And I hope we're all looking over here now. Drawing Lewis structures. You learned your own way of doing Lewis structures from your previous instructor. There are different ways of getting to Lewis structures. I'll show you my way, and it seems to work for me because I've been doing it for a long time. But the important thing, whenever you hear Lewis, do you remember what your brain is thinking? Your brain is thinking two words: valence electrons. So the most important thing is the valence electrons. So the book's got several examples. Let's make sure we do different examples. We'll do NCl3. Let's stick with the nitrogen theme here. H2NI2. Now that one has a plus charge. And we can get a third example in there if we're careful. And let's do SO3 2 minus. The periodic table you're given on tests, you will be able to see every test that I have posted has a periodic table as page 1. Every column has the Roman numeral system for depicting valence electrons. So hydrogen's got a big Roman numeral 1 above it, meaning it has 1 valence electron. Nitrogen's got a Roman numeral 5 above it. So when you're counting valence electrons, 5 for nitrogen, 1 for hydrogen, and you've got 2 of them. Chlorine has 7. There's 3 of them. Yeah, iodine also has 7. And there's 2 of them. Talk about charge in a second. Sulfur's underneath oxygen in the column that has a Roman numeral 6. And oxygen is above it. Remember, we're talking valence electrons. So what does these charges mean? These are the charge on the overall ion is plus because it has what? 1 more valence electron or 1 less valence electron than this number here? Well, let's just do a hypothetical example. You've got a species with 6 valence electrons and the atoms on the periodic table have 7. That'd be a cation. Here we have a total of 2 plus 5 is 7 plus 14 is 24. Minus 1, you have 1 less electron than the atoms brought into the game. Did I do that right? I don't think I did that right. 2 plus 5 is 7. Plus 14 is 20. Oh, my math is terrible. Oh, that's bad news on our test because we're not allowed to use calculators. Oh, 2 plus 5 is 7, plus 14. 7 plus 14, 21. Minus 1, 20. I knew I was in trouble when I had an odd number. And then, oh, this thing has 2 extra electrons. That's how it got to be an anion. So we have really 4 times 6 is 24 plus 2, 26. Okay. Next up, we're going to lay out the skeleton. What goes in the middle of the skeleton? Well, there's certain atoms that are usually not in the middle, sometimes some that are never in the middle. It says H and F are never the central atom because they can only form one bond. The only times Cl and Br and I are the center atoms are typically if there's oxygens around. They usually only form one bond. Oxygen-oxygen bonds, avoid those if at all possible. They are very rare. I cut off the rest of the textbook. Please read it. There's good tips in there. So keeping in mind, this is going to be a normal chlorine, and it likes to stick off one time. So a nitrogen is going to be central. You've seen it central before. You've seen ammonia. This is very much like ammonia. So we got a central atom, 3 bonds, each to chlorine. A good tip is to try to make things symmetrical. That will do you well. And this seems to be symmetrical. Cut it in half here, same over here as here. And don't worry about lone pairs yet. We haven't got to that step. And how many bonds did we make? Made 1, 2, 3. How many electrons are in 3 bonds? A bond is a sharing of a pair of electrons. So I never added up my original total here. We're supposed to have 26, 21 plus 5, 26 minus 6. We've got to come up with 20 more. Why don't we finish NCl3 and then move on to the other 2? 20 more. Where are we going to put them? I'm going to keep going stepwise here. I like to put lone pairs on the outside until the octets are full. Even if that's not going to give me my final answer, that's a good strategy. I have to come up with 20 more. Well, chlorine gets a full octet if it has 3 lone pairs and 1 bond. That is very typical for the halogens. That's 18 of the 20. You've got to put 2 more electrons somewhere. Please don't put it on the chlorine. You'd have an octet violation on both the chlorine that you put it on, and you'd have an octet violation on the nitrogen. But nitrogen is 2 electrons short of a full octet. And there you have it. You have your final Lewis structure for NCl3 right here. And there it is. Pink almost hides the lone pairs, but you can see them. Okay, final answer for NCl3 right there. We'll talk about, we'll do a geometry review later. Not this time, but later. Okay. Next one, we're never putting H in the middle. We avoid putting I in the middle if at all possible. So N is once again in the middle. It's got 2 H's. You can put 1 on the left and 1 on the right. You can put 1 on the left and 1 straight up. I don't mind. And 2 I's. This time you made 4 bonds. That's 8 electrons. And we have to come up with 20. We've already used 8. You must come up with 12 more. This one's going to be even easier than the last one, I think. Yep, went out of control there. All right. Hydrogen never gets lone pairs. Please don't do that. Hydrogen doesn't get a full octet. Hydrogen's in the first row. It has a full set of electrons when it has 2. So it's like a duet. Iodine, though, needs a full octet. And that means it is 6 electrons short. There are 8 electrons around this iodine. Let me show you. 2, 4, 6, and these 2 is 8. So it's got a full octet. Same for the nitrogen on the bottom. 3 lone pairs. And the nitrogen in the middle has a full octet. And I believe we put on 12 electrons. I'm not going to highlight it yet because it's not quite done. Nope, that didn't work. See if we got everything. We did. Now in chem141, they said, all right, you've got this species with a charge. But the original question had a plus up there. See that? Right there. So they told you, you have to do this. You must surround it with a square parentheses and put that plus charge right there on the top right. Chem241? I am not a stickler for the box at all. In fact, I would prefer it if you did it this way. And we have to talk about something called formal charges before we know what this means. I want the charge like the 141 people, but I want you to tell me which atom possesses the charge, or sometimes it's multiple atoms, and the total ends up being what would normally be put up here. Nitrogen has a formal charge of +1. Let me explain why. I don't know if they told you why. They told you how to calculate them. They had a formula. You take the group number, which was the Roman numeral 5, gives you a 5. You subtract the number of electrons that an atom has in the lone pairs, and then you subtract half of the electrons in the bonds. They didn't tell you why. Here's why. Formal charge is electron ownership by an atom in a molecule or ion, compared to the periodic table. That's pretty good. I'm going to bold that, make it bigger, make it pinker. And we'll move it, if it lets me. Okay. Edit it here. So nitrogen on the periodic table owns 5 electrons. So if an atom of nitrogen in the original species owns 5, it'll have no formal charge. Let's go back to our previous example, shall we? Let me see. Nitrogen owns both of these electrons. It's not sharing them, it owns both. Nitrogen owns, let's just say it's an equitable world here. There's a bond of 2 electrons between these atoms. And let's just say for formal charge calculations, you own half the bond. Half. So what's half of 2? It's 1. So nitrogen owns one there, and one there. So the total is 5. Nitrogen owns both of those, half that, half that, half that. That's 5. Down here, nitrogen owns half of this, half of this, half of this, and half of this. That's 4. It owns one less than it does on the periodic table. So it is a +1 formal charge. And this has a little more information than this. This says the species has a +1 charge, so does this. This does not tell us where the plus charge resides. And here we know where the plus charge resides. It's on the nitrogen. So please do it this way in my class. And we'll move our chem141 comment. There we go. So that's how I want to do it. I have a preference of circling formal charges, so you'll know that that plus is not like a plus in a reaction, A plus B gives C. And that's just my preference. If you just have a naked plus there without the circle, it's fine too. And let's highlight this as our final answer. Let's I'll get the highlighting done faster this way, but it's a little dangerous. Okay. Oh, I haven't saved our document yet. Don't want to do that. 241. Oh, capture. There's Mondays. Okay. Our third example, we have to come up with 26 electrons. You want to avoid oxygen-oxygen bonds, so do not have any if you can avoid it at all. And I can easily avoid it if I just put sulfur in the middle here. So our first step is to lay out, well, my pen turned itself off. It's fell asleep. We used 6 electrons to make 3 bonds. Had to come up with 26 to start with. 20 more. I think the 3 lone pairs gets us to 18. It's going to look like our first example a little bit. Oh, sorry about that. Yeah. Oh, well, if you're going to be like that, I can just do this. Sorry, I talk to my computer a lot. 20 more electrons. Fill the octets on the outside first. That's 18. Can't put any more electrons on those oxygens. Have to put lone pairs on sulfur to get to 20. There's 20. And we are pretty far from done here. Octets are good. Sulfur has a full octet, 2, 4, 6, 8. Oxygen's full octets. 141, you'd put a box on it and put a 2- on it, and you might say you're done. Right? 2- on it. I'm going to tell you why we're not done. We have to put formal charges on in this course. That's something you might not have had to do in 240 or 141. But this species has way too many formal charges. It's got every atom with formal charges. It's got a minus here. Let's go purple. I'll verify that for you. Oxygen on the periodic table owns 6 valence electrons. This oxygen owns 7. 2, 4, 6, and 1 more shares half. So 7. Every oxygen's the same here. Sulfur on the periodic table, also group 6. This sulfur only owns 5. It owns 1, 2, 3, 4, 5. That's a plus. Sulfur does not have to violate the octet rule. Sorry, does not have to obey the octet rule, and it doesn't have to violate the octet rule, but it can. And here it will. If you get an element that's beyond the second row, you can make more than 8 electrons be around it. Why is this the case? Well, electrons go in orbitals. If you have enough orbitals, you can put more than 8 electrons around an atom. Sulfur's in the third row. Once you go from the second row, which has only s and p orbitals, which you will be looking at the end of today's lecture and continuing on Monday. Second row has only those orbitals, and if you remember, there's always just one s, and there's 3 p orbitals. That's 4. You can get 8 electrons in 4 orbitals. Sulfur has those s's and those p's, and it has available d orbitals. Sulfur can have up to 12 electrons around it if, by violating the octet rule, you get the formal charges down. And all I'm going to do is take one of those lone pairs off of one of the oxygens. Say, take the top lone pair off of this oxygen, and the minus is going to disappear. I'm going to verify that for you. And the plus will disappear. So I took the oxygen lone pair off, and I'm putting it back on because you still have to have the right number of electrons. I'm putting it on as a second bond. Some of you might say to yourselves, he just added a double bond. I did not add a double bond. I made a second bond. What I did add was the second bond is called a pi bond. So you're going to review sigma and pi bonds over the weekend, please. And by doing this, yes, sulfur's violating the octet rule, but it had a d orbital available to do this, and I got rid of 2 of the formal charges. Okay? So you're asking yourself, well, why don't you do it again? I'll show you why this is the best. It's going to have a highlighter on it pretty soon. I hope I got everything. I did. This will not happen. Do it again. There's a good reason why. Take it off the oxygen, move it into the sulfur. Okay. That puts a minus on the sulfur. And this brings up a different issue. Where do you prefer having a minus charge, on an oxygen like this one or on a sulfur like this one? Keep in mind, a minus charge means extra electrons. Atoms with extra electrons are less stable if those electrons are far from the nucleus. Oxygen, being more electronegative, is better able to stabilize extra electrons than is sulfur. So we prefer this structure here over the one to the right, because more electronegative atoms are better with minus charges than less electronegative atoms. Okay. Now, before I highlighted that one, I should have made a copy, because that oxygen that has those 2 oxygens that have the minus, they don't have to be the ones with the minus. So I'm just going to make this one look like the one I just wanted to copy. Took it off, put it on. Minuses are here and here. Some ions are unusually stable, even though they've got multiple charges. And the reason they're unusually stable is they can do this, which is called resonance. Get used to these curved arrows. More and more, they become more and more important as we progress in this course. I will explain what each arrow meant. I took a lone pair on this arrow and made it a shared pair between the oxygen and sulfur. You can reword that. Lone pairs becoming a pi bond. Here, the pi bond breaks. There's a reason why pi breaks before sigma. It's weaker. The pi bond breaks and becomes a lone pair on sulfur. Process is called resonance. You get an equally stable resonance form, which means so far this molecule would spend half of its time like the one on the left and half of its time like the one on the right. But that's not a true story either, because I can do a third resonance form where the double bond is between this oxygen and sulfur. I haven't done that one yet. Same process. It's called resonance. Lone pair resonates. Pi breaks. Becomes lone pair on the other O. So in the end, this sulfite ion, and that's what it's called. Yep. Always review your 141. Sulfite has one less O than sulfate. They have the same charge. Some of this is coming back to you, I know. Some of you are saying, oh my God, that's been 5 years. What's happening? I got to remember that now. Oh, now that thing is encroaching on the molecule above it. I am a spatially challenged individual. You'll have to put up with it. Thank goodness we can move things around, right? And we have 3 lone pairs here. And we have only 2 left here because I used one for resonance. And we have 3 here. We still have this one here. And now we have a minus over here and a minus up here.
Hey, Professor?
Yes.
Real quick, what's that curved arrow called again?
It's called a resonance arrow. Oh, the curved arrow? That's
Yeah.
actually the introduction to a mechanism. It's how the electrons are flowing during resonance. That's what it represents.
Also, does it have an actual name?
In this case, resonance arrow, resonance mechanism arrow there. In general, though, mechanism arrow.
Okay, so mechanism arrow.
Yes, call
Right,
curved arrows mechanism arrows, and by the end of the semester, those mechanism arrows will be like 50% of your final exam. I'd like to, yeah, it's something I mean, wow, how can that be 50% of my exam? Right now, you're just saying, okay, that's cool. Okay, good question, thank you. And if you have a great question like that, feel free to unmute yourself and bring yourself in. Thank you, Mr. Aldebani. Aldebani. Okay, so sulfide ion, in summary, spends 1/3 of its time right here, 1/3 of its time right here, and 1/3 of its time right here. And those charges, you see them moving around. That is the best way to stabilize charges. And it looks like that is plenty for our first segment. Now, if I do long segments like 38 minutes, we're going to need more than a 5-minute break. You guys are lucky. My other class is the guinea pig, and they've already lost a video, and Zoom is working on getting it back for me. So it's going to be more than a 5-minute break for me to render this and save it, okay? So bear with me, just hang in there. We'll be back. I got to make sure I follow all the steps or else the video is not even saved. I got to stop here first, and then I've got to end here. So we'll see you in maybe 8 minutes, okay?